the plan is to cover so the so this technique matching pursuit for this Lasso formulation, and to kind of give and kind of a small kind of possibly surprising application of this called compressed sensing, where you can recover these models exactly if you assume that the model is sparse, kind of using these algorithms. And so this will kind of an extension of the lecture on so Monday with more detail. I just want to start by kind of looking at the schedule, and there's some important things coming up. So first notice, there's not another homework assignment due for about a month. So I'll try and post the regression homework before break, but it won't be due for kind of 2 weeks after break. Or at least near the start of break at some point like that. All right. So other stuff that's coming up so on Monday next week, we'll be doing stuff about cross-validation and kind of thinking about ways to evaluate these models. Even if you've seen cross-validation before, we'll talk about some of the kind of maybe why it's not actually it doesn't solve all the issues here. And in particular, we'll try and have a discussion again kind of at the end of the lecture, and I'll talk about this paper here. You can click on this link, and this links to a paper called The Garden of Forking Paths, and kind of this. So we'll talk about these kind of these four sort of cases about when you're doing gay analysis and trying to build a model, and these fallacies, and about how it's not as simple as either it's the proper way of using statistics or it's kind of is phishing. There are these states in between, and you just need to be aware of these sort of issues. So then a couple other things coming up. I'll talk about the midterm in a second, but after spring break, there's going to be due the intermediate report for your project. This is going to be so 1 page per student in the group. Okay, so if there are 3 of you, you get 3 pages. If it's 2 of you, it's only 2 pages. And this will be due at so I think the time is like listed a little bit earlier, like at so like at noon, I think, on this Monday. One of the reasons is I hope you all this lecture will be kind of a half lecture, and the last half an hour I'll pair up kind of groups, and you guys will discuss and give each other feedback. And then later on this week, I'll have a sign-up posted, and you guys will all meet with me for just a few minutes, and I'll give you feedback on the project. But when you meet with me, you'll actually you'll bring in, printed out all of your documents up to that point, the project proposal, the data collection report, and the intermediate report, and I'll kind of read through them as I'm giving you feedback. So I want to make sure it's done so you actually have it printed out, and when you're in class, you'll bring it into class as well to share with the other groups. So there'll be more details. I'll post about that online. You can look in the project document to get a preview. So then on a week from today is going to be the midterm test, right? The midterm test will cover basically everything up through the streaming algorithm. So not the lectures that are happening this week. I don't plan on testing on this stuff from regression now. I'll mainly test on that on the end term, which will mostly cover the second half of class. Let me say a few things about what is going to be on the midterm. computers, um, so calculators, or sort of phones. Okay, so I don't want you to bring in your computers or anything where you can send messages to other people in class. Okay, but you can have one so cheat sheet. So this will be one piece of paper, and you can put anything you want, anything you want on it, and so you can so you can put stuff on both sides. Okay, so if you want to work together and make something together, it's fine. I think it's good to study, to think yourself what is the most important stuff on there. If you want to take the PDFs and kind of copy and paste stuff from the PDFs into small font, that's fine. If you want to write it out by hand, that's also fine. But you can bring this in. I don't want you printing out everything in the book because it's just wasting paper. But you can make a cheat sheet to bring into your notes. Okay. So I'll expect you then to kind of like to like understand some like so like some core definitions, right? So or like some core algorithms. I could ask you to run a very small version of like the Gonzalez algorithm or one of the other kind of simple clustering algorithms. Like I'm not going to ask you maybe to calculate something kind of crazy because you don't have your computer or even a calculator. You shouldn't have to do any very hard calculations. If you do make mistakes in calculations, will kind of be lenient in the grading, but I still want you to try and make these calculations. All right, so you should be able to understand the core definitions and algorithms. You can put them on the cheat sheet. Part of the reason for that is so you can, if you don't think you can remember everything, just write it down on this paper, and this can be your notes, right? So I can't ask you to calculate complex calculations, but I can ask you to run simple algorithms to kind of look at the output. Does this output look like it's correct, or like if it's not correct. And so I looked at the midterms I've given in the past. They're probably going to be probably going to be kind of 3 questions with subparts. Okay, and so in the past I've had questions on clustering, kind of like assignment based, so hack, where I ask you things maybe to run a simple version, maybe just to look at the output. So similarity, on things like distances, can you tell the difference, which kind of calculate these simple distances between these points? I've asked a question on like min-hashing in the past, on like Jacquard, doing so like k-grams. These are things I've asked questions of in the past, right? Doesn't mean I'm probably not gonna ask everything. Oh, and also streaming, maybe compute something with Mischigrees on a very small example, right? Or so these are things I've asked about in the past. It'll probably be kind of, I'll pick probably 3 topics from these and ask questions with a few parts, right? Most students, I expect that some people will finish within like half an hour. We'll have the whole, I guess, 100. The class time is like so Some people will finish within half an hour. Most of you will finish within 60 minutes. And there's always people who kind of wait until the very end to finish, right? So it's not intended to be hard. It's intended to be stuff you should be able to kind of, if you're following along, you should be able to do these things. The questions should not be maybe as detailed or challenging as the homework, but you're going to have to kind of recall it within the 80 minutes you have to do it. Right? So I can't ask you anything complex, but I can ask you to kind of work through some of the stuff we covered. Yeah.
So you consider an upper bound for complexity being the stuff we've had on homework, like this should be easier.
Yeah, right. Yeah, the stuff you do in the homework should be bigger and more complicated versions of the stuff you've done in the test. And I can't ask you to implement anything, but I mean, I can ask you to work through an algorithm, right? A lot of the algorithms we cover are intentionally kind of very simple, and so I can give you a very small data set and ask you to do that.
Two questions. First one is, will we post any of those previous midterms or basically?
Yeah, so I'm hoping to write 2 versions of the midterm by the end of this week, and post one online that you guys can practice, right? I've not done that in the past. I'm hoping this year I will finally be organized enough to do it. I haven't done it in the past, so I can't promise it, but but that's my goal, is to get one maybe by the end of the week or like some point over the weekend, and then you'll have part of the weekend and then the TA hours early part next week to kind of go and get them. I won't plan to post the answers, but I would, you can go to TA hours and get kind of answers about what the right way to solve something is, if you're not sure.
And this has not to do with the midterm, but how will getting with you for the intermediate report kind of work, or how does that?
Yeah, so I'll post more details about that. I will post forget how many exactly it is. It's about 50 projects this year. I'll post something like 60 time slots, and then there'll be a way to sign up for them. Each group will get 1 time slot, and then you'll come meet with me in the office. And they'll try and be over a variety of times, including kind of like after class on the Monday and Wednesday next week, because I know not all of you are on campus every day, but I'll try and make them over the Monday and Tuesday and Wednesday of that week. Okay, great. So let's get on with the lecture. So we talked about Ridge and Lasso regression. Okay, and so the input here, was some data set x, y, where x is going to be n data points each with like d dimensions, and y is going to be just a vector in Rn. And the goal, the goal then for ridge regression is going to be to I'll call this something else. So it's going to be to find the R min alpha in R d plus 1. Okay, and so I'm going to assume that x tilde equals, this is the all one vector, and then x. Okay, so actually let's just put the x tilde here and just call this one x, just so the notation is a little bit simpler. Okay, and so then it's going to be the sum over I to 1 to n of all of the data points of the recorded value yi minus some dot product between some vector value xi, which is now d plus 1 dimensions, and alpha squared plus some s term. This is alpha squared with, so with the 2 norm, okay, so the first, there are 2 parts here. One is this least squares term, while this part here is, this part is the model of xi, so I'm building some model, some linear model of this input value xi, and I'm seeing if it matches, how close it is to matching yi, and I measure the error in terms of the squared distance. And then I also have this so is like regularizer term, where there's some penalty which says how much I weight the regularizer versus the least squares part, and it takes this alpha that I'm trying to find, this is my model, and I want to want this to have a small norm. That's why I say if this is small, then the model is going to be more simple. Okay, so so this was the this was for the ridge regression, and I'll denote the solution with alpha sub s with a circle superscript, and then if I do the Lasso formulation, I'll alpha s, where I have a diamond instead, and this will be r min alpha in r d plus 1, the same as before. The least squared term is going to be the same, but now the regularizer here is going to be just an L1 regularizer instead. Okay, so these are kind of these 2 algorithms that are going to have a bias term. I'm going to bias towards these simpler solutions, but otherwise try and minimize the squared error. And I kind of mentioned to you that this is going to generalize better on unseen data if I pick S correctly. Yes?
So alpha corresponds to all the coefficients for the model, right?
Correct. That's right.
Just a vector of.
That's right. Yep. So I'm multiplying every data point, xi, is going to be a d-dimensional vector, and I've appended a 1 to it, or prepended a 1. And I'm taking a dot product. What is a dot product? The dot product is the sum kind of multiplying every corresponding value, right? So I'm multiplying the coefficient by the value, adding them up, right? This is exactly this linear model. A dot product is this really powerful kind of simple notation that captures a lot.
And then S is going to be learned through cross-validation.
Yeah, right. So you can learn S through cross-validation, yeah. Yes, okay. So, well, I want to start by, the goal today is to kind of, I told you how to solve for the ridge regression formulation before, and I mentioned this Lasso one induces sparsity, but I didn't really tell you how to solve for it. I said, maybe you can do gradient descent if you're careful about these places where the gradient isn't defined in the L1 norm ball, but there are other ways that people often use. Okay, so the first step to doing this is to understand that there's a different interpretation of these 2 problems. I can also say, and I can define this alpha t 0, and this will be the arg min alpha r d plus 1. So this is this, okay, and again, I'm going to write so this the same as before. Okay, but now I'm going to write the regularization in a different way, in a hard constraint, such that alpha, the 2 norm, is going to be less than or equal to t. Okay, so this is now a hard constraint. I'm saying the norm of the model, the L2 norm of the model, has to be, less or equal than t. It's not just, But then, given that this is true in this solution space, I'm going to solve the least squares problem exactly, right? So I'm not putting a bias in here, I'm just constraining the solution, right? And so similarly, I can write this for the Lasso version. Plus 1. Right, but now it writes such that the L1 ball is less or equal to T. Okay, so now this constraint is L1 constraint. Okay, and so I'm going to argue that these are equivalent. So basically, for all choices S, which are not, yeah. So for all choices S, there exists a T. So alpha of S0 equals alpha of T ball, or alpha S0. So the diamond alpha of T, so diamond. Okay, so I can do this for either. They're not necessarily going to be at the same point, but for either the ridge or the lasso, or the lasso formulation, for every choice of S, I can determine another choice of T so that these two formulations will give the same answer. Okay, there's this big space, there's this D plus 1 dimensional continuous space of answer. If I fix the data and then I solve for S, this gives me some vector value, and I'm going to get the exact same value for some choice of T. Okay, so this is true because, well, I can solve for, just think in the ridge regression case, I can solve for the unique solution for alpha of S of, in the ridge case. I can do this for the Lasso cases, so as well as we'll mention. But I can solve for that. Then I can say, well, I can do something like let T equals the norm of alpha S. Right, so I can let T be equal to, after I solve for alpha of S in the ridge case, I can just set the value of T to be, so it's equal to this. Okay? Now if I plug this into this formulation, well, I know that this value of alpha S is going to give me some value which I can decompose into the sum of square terms and this term with the penalty. And it's going to have smaller costs if the penalty is smaller. Okay, so that means if I make the norm larger, there might be a better solution with the norm that's larger, but that would be ruled out because I've set T equal to this. Right, so I've set this equal to alpha of S0. So I've set T equal to this value. So anything with a norm larger than this is going to have, I might have a smaller sum of squares term, but it's going to have the norm of the alpha value, which is too big. Okay. So anything anything that has a smaller norm of alpha, right? So then I can also consider things that have a smaller norm for alpha. That would be okay if the norm is smaller than this value. But if the norm is smaller, well, then it's going to have a larger cost here. Because if the norm was smaller and the cost was smaller, I would have chosen that for alpha of S. That would have been my solution. Okay, so I can't do a better solution than alpha of S if I set T equals to this. And so as S gets smaller, I penalize the norm less. I'll find a larger norm solution. And that means I'll set t larger. So as s gets smaller, t gets larger, and vice versa as t gets smaller than s gets larger. So there's this kind of one-to-one relation, almost, maybe not one-to-one, but in this direction for every s that maps to some t, up to some point where you find the best unconstrained solution. Right? And so as s goes up, then t goes down. So this relation is monotonic. Okay, so I can also, posing these, and the same argument works with Lasso, assuming I can solve this formulation, which you can show you can because it's convex. Okay, so that means these formulations are effectively equivalent to each other. As long as I'm choosing s or t with cross-validation, then I can pose it in either of these ways. Okay, so I mean, for the ridge regression, I have a simple solution for the top formulation. So I usually pose it that way. For the lasso, it's actually easier to think of it in this formulation. Okay, where I have this hard constraint. Yeah.
Is the reason for changing the constraints that way is so that, is it like easier to compute?
So
the
it'll
second
be,
part as opposed to the first one when you change the optimization constraint?
so I mean, the ridge regression is easier to compute in the top form, right? So I usually write down that one. I mean, you can, if you're doing, yeah, because it's a single. Either I use gradient descent, and that's a single convex cost function that I just optimize over with the gradient. I can compute it, I solve for it, or I have the closed form solution, right? In the ridge case, there'll be two algorithms that we're going to discuss. We're going to, the first one will go in more depth, match and pursuit. It'll actually use the top form, but there's another one, but that one is not going to solve it exactly. If you want to solve it exactly, it's easier to use this bottom form.
Okay.
And what you actually do is you start with a really small value of t, and then you gradually increase it, and the solution kind of grows, and you can solve it exactly in that way. And so but this one will also give us insight into why the algorithm works the way it is, and what's going on. Okay, so let me try and do this here. Okay, so we're going to, see if I can copy this. Okay. Okay. Cool, okay. I've never done that live before. Okay, so I want to look at this L1 constraint on the norm, and so I'm going to try and draw a picture myself so you can see how it develops, and then I've got a pre-drawn picture on the next slide that will look a little bit nicer. Okay, so but I want to think of some space here. So I want to I'm going to draw some d-dimensional space. I'm only going to draw some two-dimensional space. And in particular, this is going to be the space of alpha. Okay, alpha is going to be a vector, right? So I can think of alpha 1 and alpha 2 in this space, right? And so then if I think about what does this constraint look like? It's an L1 ball, right? So what that's going to look like, what this constraint here is if I put some value of t, okay, and then I'm going to put the L1 ball. Remember, this looks like this. Okay, so now we can say that alpha of t kind of diamond has to be in this space. So I'm in the constrained version, it has to be in this ball, right? This is what's in, right? Whereas if instead I did alpha to, so let's see, alpha is less than t, let's instead cross out the square term here. We can move that to make that the square root of t, but to put them in the same picture, I'll just have that be t. Okay, so now I'm going to have this L2 ball, and the L2 ball is going to look similar, but this is now some disk, right? It's going to look like this. So now the solution for alpha of t ball has to be in this space. Okay? So these are different constraint spaces here. Okay? And so again, this is somehow supposed to kind of infer that the model is going to be simpler. Someone asked about what if we wanted to have some some model that was as high norm as possible on Monday, right? And a very high norm model could have two correlated terms. One is positive, one is negative. One is positive, one negative. That could be really far down here, and they would kind of balance each other out in the actual prediction. But that's kind of less simple, it's less nice, it's less intuitive. It's probably more susceptible to noise. What if those two are not quite correlated? Then I can have these huge swings, right? And remember that this corresponds with the slope of individual variables. So if I want these variables to be kind of stable with respect to the x values, I want these to be small. Okay, so that's one useful thing of looking at this picture. Okay, so the other useful thing is that I can think of having, let's draw this here, let's call this alpha star, where we'll say alpha star is going to be our min alpha and r b plus 1 of just right, so just the squared term here without any regularization on it. Okay, so let's say if it's inside the ball, it's easy, right? That's inside the ball, it's easy. If it's outside the ball, well then I need to find the best solution inside the ball. Okay? And I know this is a bunch of squared terms. It's a d-dimensional equation in alpha, or d plus 1 dimensional kind of alpha, and it's a bunch of squared terms. And these could be correlated based on the data, but I know it's squared, so this means it's this is going to look kind of, it's going to look kind of alpha star. So it's going to look like some form of parabolic, right? But high dimensional parabola, which means it could have some skew to it, but that means that if I look at the level set, right, if I look at some kind of fixed value and everything below it, right, everything in here, this will always be some form of ellipse. This is what this means. Okay, there's some ellipse like this. Okay, so let's say these elliptical shapes look something like, let's say it looks, let's not make it too crazy, that would be too hard. Okay, so let's say they look, so something like this, right? So these are different cost functions for just the sum of the squared. That's the minimum cost. So it might not be at 0 at the bottom, the overall cost function, but it's kind of growing out of here. Okay? Okay, and then I want to find the minimum cost when it hits these balls. Yeah.
So then any intersection with any other part of those level sets is a suboptimal solution to regression.
Yeah, so any point on a level set here is going to have the same sum of squares cost, just the kind of the cost with the data, right? And then, but they have different in terms of like this, the distance from here, their L1 or L2 measures kind of this regularization cost. And now we're looking at this hard constraint version. So So we can see that eventually, you know, it's going to grow. And then, okay, so what's going to happen in the case of the L2 ball, it'll hit something right here. Okay, so this will be alpha of t ball, right? So this point where this level set hits this ball, okay, where it first hits the L2 ball. Okay? Okay, so what's going to be special if instead I use the L1 ball is where is it's going to hit? It's going to do something like this. Okay? And instead it's going to hit right here. Okay, and so this value is going to be alpha t, okay, in particular right here. Okay, so what's special is happening about this?
You just lost one of your coefficients. So
Yeah, so this alpha 2 coefficient is exactly 0, right? Because I hit on the corner, this corner point right here, it's the alpha 1 coefficient is t and the alpha 2 coefficient is exactly at 0. Okay, and what's happened is this L1 ball is kind of is pointy. It has these corners coming out. And in high dimensions, this is even more kind of profound how kind of pointy it is. And so if I hit on exactly one of the corners, which happens at the axis, I'm getting all the coefficients are 0 except for 1. Okay? If I think of this as actually being in 3 dimensions instead, so there's a point coming out here, right? There's a point coming out of here and then going in as well. Then if I hit on this ridge here, I could have hit this ridge as well. That might also be a common thing. Remember now the ellipse might be at some weird angle through here. Well, then I'm going to have alpha 1 and alpha 2 have coefficients which are non-zero, but alpha 3 coefficient will be 0. So I'll still get some sparsity. I might not get them all except one sparse, but I'm going to get kind of some number of them are probably going to be exactly 0. Okay, so this is what's happening with the lasso. By using this L1 constraint, then I'm going to get I'm going to induce sparsity. Some of the coefficients are going to be, the optimal solution for them will be exactly 0. That means that I don't say they don't factor into the model at all. Right? Yeah.
So I'm just trying to fully understand this. So when you had alpha star, you're saying this is the minimum alpha without the constraint, and it
Correct.
exists at some point.
Yes.
And so when you add in the constraint, then you're going to have some intersection with alphas with the constraint. And that's where the parabola hits the circle.
Yeah, that's right. Think of this sum squared cost function is going to be, that's the minimum, but it's this parabolic thing coming out here, right? And I want to find the lowest cost in this parabola such that it hits this ball. I could write the cost function as this kind of function coming out of the plane for everywhere inside this ball, but then everywhere outside it's like infinity, right? I said I can't do that, it costs too much. And then I want to find the smallest, the lowest point. And so for the L2 ball, the lowest point is here, but for the L1 ball, it's right in the corner. And things are going to tend to be in the corner.
So if alpha star is inside of the ball, you just choose alpha star.
Yeah, that's right. Yeah, so if I set t large enough, then effectively I'm not putting any constraints on. Right? But it's interesting when I set it to be kind of smaller. Right? And so most values of S will give you a solution which is going to be, so it's going to be smaller than containing alpha star. But if I set S like really small, I might end up getting the same solution. Cool. Okay, so this is kind of the picture of why lasso induces sparsity and kind of what's going on with this. All right. Okay, here's the slightly nicer picture in case you couldn't read what I wrote before, but kind of the same thing is going on here. more precisely, you know, again, alpha t is, you know, diamond is with the lasso solution is hitting right in the corner, and alpha t 0, the ridge regression solution is hitting someplace else. There's nothing kind of constraining it to be at the points that have 0 coefficients. Okay, but they're still both getting the same effect of kind of regularizing the model. Alpha kind of, okay, well, oh, yeah.
Could you use a different norm to make it even pointier?
Yeah, so that was the next thing I was gonna ask you guys. Right, so what would be a different type of norm that'd be even more pointy? Alpha, so if I set the p-value for the norm, which is 1 or 2, I can set that to be something like 1/2. Right, let's draw this here. Right, if I set, if I did alpha 1/2, then that's going to be a norm that looks like this. Right, it's going to be even more pointy. Right, it's going to come in here. I still could hit inside of here, right? I could angle the ellipse so it kind of curves in and hits here, right? But it's going to be much less likely, right? The problem is, so this constraint is going to no longer be, it's going to no longer be convex. So this causes problems basically any way I try and solve it. I basically, you know, ideally, what you really want to do is I want to use only k, like 3 different coefficients to solve it. What's the best solution with 3 coefficients? This is the L0 constraint. Okay, I can do that, and then it's basically kind of it's free if it uses at most 3 things, and it's infinite afterwards. That's kind of, I'm moving this further and further in, essentially. The problem is this becomes kind of it becomes a combinatorial problem instead. And there's basically we don't know how to solve it without trying all the different combinations of 3 and then just seeing whichever one is best. Which you can do that, and that's an okay thing to do, but it becomes much more expensive because you're doing all kind of D choose 3 combinations. Okay. And if I tried to do gradient descent, even restrict it to within here, the cost function is not constrained if I use the first term relation, and the second one, the solution space is not constrained. So either way, the kind of gradient descent is not, I don't have any guarantees about what it's going to end up doing. It could easily get stuck in the wrong spots. Yeah, but that's a good question, right? So ideally, that's what we would want, but that becomes hard to solve. Yeah.
So back to a question I had last time, and maybe this changes in higher dimensions, but it does look like your lowest values of your ridge regression would correlate to 0 values in Lasso, at least in a 2D.
In the 0 values. What do you mean?
Like the lassos, like if we run Lasso and let's say like your index 3 and 5 are 0, those would index 3 and 5 would also be the lowest values that you would have for ridge regression. That's what it looks like in this 2D version.
So there is this heuristic that you can solve ridge regression, and then you can basically decide, well, if this is small enough, if the coefficient is small enough, then snap to 0, right? So I can round down a bunch of things to 0. Yeah, so this is a heuristic that some people use in practice, and in some cases it actually works pretty well. In other cases, it does not give you the right answer. So it's, you know, sometimes it's some, you know, so you could think of getting. So I could think of, so what if my cost function ended up looking something like this, and I could think of this being, right, so I ended up with this solution here.
Right.
So I might try and round down to here. Just think of it, maybe if it's oriented the other way.
I kind of get what you're
Yeah,
saying.
if it's oriented
Right.
this way instead, actually the cost might increase a lot to go there. It's
Right.
just very tall and narrow in this direction, right? So it may have one of those sort of issues, right? So you don't, there might be a way you can actually use, you can look at that and try and have that guide whether you round to zero or not. And then there are variants of this, right? But it's kind of just using that value to decide whether to round to zero or not kind of is ignoring this information.
Right. Second question, would a infinite
L infinity ball.
would that give you the best single regression solution, or like simple regression, like would be like a single variable?
Oh, so I mean L2, like if I use an L2, like an L2 ball instead of an L1 ball, I'm already not going to get sparsity, right? If I'm using an L infinity ball, I'm actually probably going to be, yeah, I don't know, that might induce sparsity.
Because it seems like here's the
Oh,
idea, is that if you get like all of them be zero, except for one would be,
Yeah,
one would have a value, and then that would be like the best simple
Right.
regression
right,
solution.
but it would only give you one coefficient.
Correct.
It would always give you exactly one coefficient. That's the downside. So if you always wanted one, but you can also do that by isolating each coefficient, solving for each of those, and
Right.
see how that works. So you can solve for that, but it's not clear how to generalize beyond finding just one
This
coefficient.
maybe not a good way
L
to do
infinity is a cube, right?
That's a cube. I'm putting the cube.
So isn't it d minus 1 or d dimensions that are only 1 and 0?
Well, think of in this picture, right? The L infinity ball looks like this. This puts L infinity ball, right?
So you rarely hit a midpoint of a plane.
Oh yeah, good. That's right. I was thinking of putting it on the alpha norm right here. I'm almost never going to hit on any sort of corner.
Oh,
Yeah.
okay.
Yeah, good. I'm almost always, I'm in here. I'm going to hit kind of up here.
It's bad. It's not sparse.
Yeah. So this will give me something even less likely to be sparse than the L2. But as soon as you move above L1, you're anything above L1 is no longer going to have corners, and you might get something very close to zero, but it won't be exactly zero anymore. Even if I do L 1.001, it's no longer going to have corners, so the solutions I'm going to find are going to be right off of that point, probably. Yeah, so this isn't going to help. So L1 turns out to be just the perfect thing to use.
Can I get a reminder of why is our objective inducing sparsity in this domain? What does that benefit us?
So why is sparsity good? Well, it's simpler now in two ways. One, the overall norm is smaller, so the slopes on average aren't very large. But also a bunch of the slopes are exactly zero. I say, I'm not using this coordinate at all. It'll give me models that I could have 100 kind of variables of features that I've kept track of from my data points. And I say, look, I can find a good solution that only uses 3 of them. When you like that more, right? It's gonna be faster to evaluate, potentially more explainable to someone. So it's simpler in this way. And we'll see. Hopefully, I'll get to it. You can sometimes recover an exact solution of a model. Okay. Okay. Now, again, I'll just give a warning. Don't assume that this gives you necessarily the only coefficients, the only variables which tell you this. They may be correlated with other ones which are actually causal. So it's not giving you something kind of implicit. But it's a good starting point for that, though. And it's a good initial guess, but don't use it as kind of a panacea. Okay. All right. So let's talk about the simplest, easiest way how to actually solve for this. And so this is called the matching pursuit algorithm. And so let me just write, I have it up here. I'll try and explain it first. And so this will, on unless there is if there is a very simple model with noise, there's situations where this can actually find the optimal solution, but in general, it does not find the optimal solution. It's kind of a greedy approach, okay? And what the idea is here is basically it's going to be kind of similar in spirit and greedy like the Gonzalez or the K-means plus algorithm, that I'm going to start out by having like some, basically I have some like values I've recorded, my observations y, and this is, I want those are things that as I pick more variables, I'm essentially explaining more of that observation y. And so these are when I have 0 coefficients, if alpha is all zeros, then I've explained nothing, and so this is my residual. The residual is everything, right? All my observations I've not explained, and what I want to do is keep adding adding coefficients, and I want to explain more and more of the observations y. Okay? So what I do, and this is the key step here, is I'm going to pick this value j is indexing kind of a column in X, which corresponds with one variable, right? So I want to think of having some data set X, right? This is X, and this goes from D here and N here. So I have N data points. Every data point is a row, and I'm going to say that a column is xj. That's all the kind of the explanatory, the jth explanatory variable, what all those values are. Okay? And so because I'm building a model which is linear, the one I want to choose first is the one that's going to be have the most kind of the most correlation with my residual. Okay, so let's actually, that's what I should have done here. Let's do this. Wow. Okay, well let's okay, so let's look at this picture again. Okay, and so I've got some. This is my what the best model is, and so kind of think of this is in a. Okay, this picture was not helping the way I was thinking. All right, so instead I want to think about this in this the space which is now Rn instead, this n-dimensional space, where I basically have x1 here, x2, and these are the different these are the different kind of these are the different data points I have. Okay, and so when I look at a column xj is going to be so this is so these are the data points, and so xj is going to be an n-dimensional vector xj, and let's say this is x7, this is over here, and this is x2, and also in here is going to be y. These are the observations, right? This is an n-dimensional vector. This is Rn. And so if I can find the xj where it's most correlated with it. So now I want to think of these, they're these n-dimensional vectors. That means this is a vector and this one is a vector. Okay, and I want to find the one with the maximum dot product. Okay, The dot product, well, because R, or initially y is equal to R, because this is not changing, I can pretend that it's a unit vector. And then I remember the dot product is actually the length of xj when it's projected onto there. And so the one that has the smallest angle is going to be the one, or times its length, is going to be the one most correlated with the actual observations I have. And that means that when I take the dot product with that, it's going to explain it in this n-dimensional sense. I could have another one which is correlated, say, in some of the dimensions, but not another. So when I try and find the best representation in this space, then kind of it's going to give me this residual in one of the other dimensions, right? So what's happening here is I can extend this xj, and then I'm projecting y. My prediction with just one coefficient, one feature, has to be a linear combination of xj. So I pick a coefficient so that I take y and I find the closest thing, and what's left over is the residual. This is an n-dimensional space. Okay, so I basically want to find, because I can choose whatever coefficient I want, I basically get this projection onto this space. So I want to find the one that is kind of the smallest angle there, and that's captured by this dot product, by the norm of this dot product. Yeah.
That was actually my question. Is there a more efficient way, I guess, to get that angular distance information, or is the dot product driven with the
yeah, you're probably right. In really high dimensional space, it might be useful to build, say, locality sensitive hashing with the angular hash function. Yeah, so typically, yeah, this might be faster. I'm guessing someone's made this observation before, but for very large problems, this might actually be useful. Usually, I would think of it as just if you were to implement it for something on the scale of your homework, for instance. Forget if I'll ask you to do this or not, but you can just check all of them. But if you want to speed this up, yeah, you can do the kind of LSH for this. Yeah, because these xj are going to be fixed. The r is changing every time through here, but xj are, so you have a different query, but a fixed data set, right? Good, and so then once I pick it, then I want to choose this alpha, right? If I don't have this regularization term, it's actually going to be a projection, but with the regularization term, it'll be something else. But if I'm solving for a single alpha, right, this value is actually, it's just some one-dimensional function, okay? So what's going to happen is there's going to be, I'm going to be picking an alpha along here, and it's going to be the sum of a parabolic cost function, right? This is basically the sum of the squared errors plus some L1 cost function. So it's going to be the sum of these two things, but it's going to be convex, and I can solve it using. You can write down a closed form for the solution. I wrote the norm here, but you can actually factor out all the terms in the norm and just solve for the alpha value. You can just, it's a bunch of one-dimensional terms. Okay, so I can solve for this exactly, then I subtract this off this residual, and I just repeat. So I pick one coefficient, I solve for what the value should be, then I remove this effect, right? Then what happens after this step, this value y here is actually just over here. So I've taken, this is now the residual after one step. And so now I want to pick, now the right solution is x2. Right? After I've solved for this, the residual from here, now I'm going to pick x2 in the next round, and then I might fit it exactly, and I don't need x7 down here. It could be negative. I could have actually, x7 may work pretty good too, because I can have a negative value, a negative coefficient. So x2 and x7, maybe to pick either of them. That's why it's kind of not, not saying it's, x2 is definitely better than x7.
Is alpha scaling the vector
Yeah, alpha is scaling,
It's
right?
just moving it up or down.
Yeah, it's a
based
linear
on-
combination. There's this one-dimensional function, and I'm kind of choosing how much the effect of xj should be to represent it. If I don't have this term here, that's exactly going to be a scale of xj. So it's about 1.3 times xj is going to be pretty close to the value y, the vector y, in all n dimensions.
So is this giving you a different result than Lasso, or is this giving you the same result as running Lasso?
This will sometimes give you the same result, but if I set, I've not really figured out the right way to set S here. If I chose S correctly so that I got exactly one coefficient, then this would give me the right result. But with two or more, if I set it larger so I get two or more, there's some sort of thing where I've chosen the first one and then that will influence how I pick the second one. But it could have been that there was a different pair that combined to do better. So I've kind of have some bias because of the sequential ordering, the greedy ordering I went through, and that might not be optimal.
And is this just more efficient or easier, or like why would you
This
run this?
this is a pretty easy algorithm. There's another algorithm called Lasso regression, which I'll kind of describe loosely now, without all the details, which will give you the exact solution. But it's much more complicated. I think I wrote it in the notes, and it's pseudocode, which is about 20 lines, right? Where this is like 5 lines, are all pretty simple steps. Where other ones, several of the lines are solve this linear equation, or kind of, so it's kind of a more complicated process. Right, so this is matching pursuit. You can use it with or without this regularization term. It's also called forward subset selection because I'm moving forward and incrementally adding one kind of a subset, increasing the subset of the coefficients or the features I'm using. There's a version that goes backwards and tries to remove them one at a time as well, but it's less common.
So the S here is the same S from, or I guess that's the.
Yeah,
thing
it's
we're
in,
choosing
it's
from.
in, so S is okay, right? There's this formulation from Lasso. So I've chosen some S to tell me how much to penalize the kind of size of the model.
So why would you ever not use S in the matching pursuit?
Oh,
I guess I'm confused. Like,
yeah, it's slightly harder to solve it with S. Maybe I don't know what the right S is. And actually, if you have really a lot of data, you might be better off choosing kind of assuming S is 0 is probably pretty good. There's a Bayesian interpretation of this where this works as the prior. There's a prior on having a small norm, and as you get more and more data, you should trust your prior less and trust the data more, and means you should kind of make this S become smaller. So it's so if you have lots and lots of data, you might say, well, I don't even need a prior anymore. It's still okay, but you'll find out if you kind of say what is the right value of S as you get more and more data for the same complexity of a model. If you fix the model and get more and more data, your S should actually go down and eventually becomes very small because the data is telling you the right thing. But if you don't have a lot of data, this becomes more important. Or if you have a really high dimensional model, even if you have a lot of data, you still really need this. But eventually, as you get, trillions and trillions of data points, this S can be even with high dimensions because you can fit exactly what's going on. Yeah. Yes. So what I want to say, there's another model called orthogonal matching pursuit, and this is generally used more with the ridge, right? So this is now a version that's usually using ridge, and the difference here is that every step, it's instead solving for the full alpha on J And with ridge, I can do this. I've got a closed form here. Okay, so this is a way I can use the ridge regression, but still by stopping after some number of steps. After 10 steps, I'm only going to use 10 coefficients. But I can use this closed form solution at every step here, and this avoids the issue of if I chose a coefficient incorrectly initially, maybe it's too large initially because I tried to use it as much as I could, it was more than I should have used it, then it just reassigns that value. Okay, and this is called orthogonal matching pursuit, and there's an interpretation in the previous slide where you're making an orthogonal move every step, and that's where the orthogonal comes from. But this is harder to do with Lasso because, again, it just brings us back to this problem, just a smaller version of it. Okay. So I want to use this picture to explain, this algorithm, least angle regression. And I just want to explain this for just a couple minutes, and then we'll talk about compressed sum. Okay. So least angle regression is like forward subset selection, like matching pursuit, except what it's going to do is it's going to it's basically matching pursuit while increasing the value of t. So I'm going to now use this constrained formulation, and I'm going to keep adding coefficients one at a time as I'm increasing the value of t. Okay, so let's say I start with alpha star, and I start with t going to be, so it's going to be very small. So what happens if I make t here so it's very small, kind of infinitesimally small?
And your alpha is close to 0.
Yeah, so alpha is close to 0, and in particular, it will, if it's very small, I will always have one coefficient. I will always choose exactly one if it's infinitesimally small, except for like some weird tiebreaker cases. If I have some very strange symmetry. Okay, but if it's very close there, this ellipse is going to get very close, but it'll be closer to one than the other. Only as it gets larger am I going to take more coefficients. So I'm going to start with exactly one coefficient, a very small t, and I'm going to grow t until at some point it's going to say, well, now the right solution has two coefficients instead, right? And this is going to happen maybe as I go out, like at some point out here, if I make this large enough, then maybe this ball, or this ellipse, it's not a perfect drawing here, but it might move slightly away from the corner at some point. Okay, and what we actually know is that for all values of t between here and until it moves slightly away from the corner, well, it has to have exactly one coefficient, and we know which one it is. And that means as we build this model, it's this L1 constraint is linear. It's a linear system of what the model is, and you can actually solve for every value of t. It gives you an alpha of t. That alpha t becomes a linear equation of t, and you can actually figure out and solve for this point where it moves just off the corner. And at that point, you know, okay, it's going to use two coefficients now, and then you can write this down, these two coefficients, as a linear combination of t. And as they increase, we know, like in the first one goes up is like in this span here, kind of alpha of t is going to be 0, 0, up to some value, this is going to be j star 1. So the coefficient is exactly t, because I know the norm is t, right? And then when it's the second one, well, it's going to have two values, and they're going to be increasing, but at a rate where they sum to t. Right? So there's linear equations that govern this as a function of t here. Okay, and I can solve for these, and I can solve for these points where this happens. Okay, and so what this does is it gives me the exact solution. You can kind of see how it works, but you see it's more complicated. And it gives me the exact solution for every single value of t. So then if I want to do cross-validation, I've already pre-computed every possible kind of coefficient value. Because I've written these actually as a set of these kind of piecewise linear equations. The complicated thing about this is to do this correctly, sometimes a coefficient will grow large and then go back down. At some point, it might be increasing, and then it may go negative again. It'd be decreasing, and then it will hit 0, and it will snap back to 0. Okay, and there are weird cases where there are an exponential in D number of critical points, where it actually, you have to solve this equation. These are pretty rare, weird conditions, but they could happen, right? So this algorithm might take a long time, but in general, you can run this basically kind of in, I think in, like, if that doesn't happen and you don't have too many things snapping to 0, then it's like almost linear time in the size of the data. It's just a pretty complicated algorithm, and so people typically don't use it for that reason, but it is available. So you can solve Lasso exactly if you want to. Okay. Most times people use some gradient descent approach instead, especially stochastic gradient descent, things that are scalable for lots of data, or something based on matching pursuit, or there are a variety of things in between. Okay. Okay. For the last 8 or so minutes, I want to talk about this compressed sensing problem, and just give you kind of a sense of how this works. Okay. So this is kind of an example where Lasso kind of is like very powerful in what it can do. And this came about, I mean, this was, I think, only about 15 years old, people made this observation. This kind of revolutionized what people and how a lot of like, how like a lot of signal processing works. Okay, so the idea is there's some signal, okay? This is some signal. It's going to be, and in this case, we're going to look at a simple version with bit vectors and so forth. But you can generalize this; it just gets more complicated. So it's going to be a d-dimensional bit vector, and this one is unknown. Okay, so I want to try and recover this bit vector. This is going to be my model, right? So this is kind of like the alpha here. Okay, so the alpha model is going to be the true model that's, say, generating some data is going to be all zeros except for some coefficients are 1. Okay? And then I'm going to have some way of these observations. This is observation I. Right? So yi is the ith observation. How do I do it? I'm going to do some sensing matrix. Okay, so I'm going to have that this S is going to be this. Sorry, this is let's see here. So I'm going to have this observation. This is my observation, and this is going to work. This is I'm going to have this is length n. Okay, and there's going to be some signal that's going to be a length, or some signal with this length d, and I'm going to sense this with a matrix that's more representative. This matrix is going to be x, right, which is n by d. This S should be okay. So this is the signal. I'm sensing it, or I'm doing some transformation, and every observation, right? So I'm going to have some xi. It's going to give me some value yi here. Okay, the value, remember this is the vector up there, it's a bit vector. X is going to be this vector with zeros, minus ones, and plus ones. And for this, I'm going to fill this in so it's random. So it's a uniform 0, minus 1, and plus 1. In this case, this is basically the right thing to do. There are variants that work well as well, but so this is a random observation, and I'm going to get some value in this case, and that's a dot product of s dot xi. It's going to give me yi, and it's going to add up. If there's a 1 matches with the 1, I get a 1 here. If a 1 matches with the minus 1, I'll get a minus 1, and if a 1 matches with the 0, I get a 0. Okay? And the end result here is 2. So I get a value 2 here for y. Okay, I'm going to do this n times, and then I want to recover s. Okay, so the question is, so if n is bigger than d, then for a long time people just use just ordinary least squares as a way of recovering s. That's kind of your best guess in some way. But what if d is greater than n? Okay. If s now could be any continuous values, then this is ill-posed. There's a null space of solutions which all give you the least squared error. Okay, but if even with this is without noise here, but you can do some other stuff with noise. If d is bigger than n, but I know s is sparse, I'm going to say this is k sparse. So I'm going to say, but k is going to be k is bigger than n. Okay, so n, the number of observations is small, but it's bigger than the number of actual 1 bits. Okay, so if it's sparse, meaning there's not a lot of 1 bits, and if I have more than this, I can sometimes still recover. Okay, I need k, in general you need k about n times log of, I think, n over k or something like this. And there's a coefficient in front, and k, this coefficient might be between 2 and say 20, depending on the algorithm. So matching pursuit is not the best algorithm, but if it's like 20, then matching pursuit still works. There are fancier things that work even better. Okay, and they can get down to maybe 2 in the noiseless setting, but they even work if there is some small amount of unbiased noise. You can still recover s exactly. Okay, matching pursuit, and there's an example which I don't have time to do, but I think this example is worked out in the book, and you can go through, and this is set up so matching pursuit actually works. In general, you need the day sizes to be larger for things to kick in, but this is an example where you can actually get matching pursuit to work. And so what you do is you first pick, I'll just do the first step here. This is my residual, and so I want to pick the column which is most aligned with this. Okay, and it turns out that column 9, there are 10 columns, I think. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 9 is pretty well aligned. Okay, so this one, and this one line up with these. Okay, it does not completely explain the model, right? But it goes away towards explaining. It explains the second, or the fourth and the fifth one exactly. It partially explains the sixth one, but it adds another term so that this residual after one step is going to be minus 1, 0, 0, 0, 0, minus 1. Right? So I've reduced the residual of y to this by using the 9th coefficient. And then I apply this again, and I'll reduce it a bit further, and so on. And it'll eventually exactly explain it. I've set this up nice so it exactly explains it, but kind kind of in, if you make D or n large enough, eventually it will guarantee to work, even if n is less than D, as long as it's sufficiently sparse. So okay, so let's stop there. You believe, so let's give an example.